Hello, my name is Kanyatutha Gisanatutha.
My name is Nashanun Janthap.
My name is Islayut Khemjan.
In this project, our group study about stain of perforated applied section in co-form steel of storage lag. This is overall content in our project. For the first introductions, automated storage retrieval system ASRS and steel storage lag, which are frequently made from co-form steels due to up lightweight, high strength, easy installation, and no need for merge, are one of the commonly used industrial for storing goods and products. In this project, considering about allowable load that influence to apply section in steel storage lag, which based on AISI and IMI standard. The result of all allowable load can use to reference when selecting the apply section in the storage lag. For warehouse industry, for the literature review, American Iron and Steel Institute is the American standard that is used to calculation to determine whether the co-form steel is to standardize. The process in this calculation must depend on the theory that this standard requires. The specification include design provision for two cases about allowable strength designs and load resistance factor designs. In this project is including about population contributions, the manufacturing institute. Specification recommend using an effective area method and taking into account the impact of perforation on the strength of columns. For the AISI standard, it focused on key topic about nominal load. In this case, it have about T failure, fractional bucking state, torsional fractional bucking state, and the torsional bucking state, and the nominal moment is focused on T strengths, about section strength, lateral torsional bucking strength, and distortional bucking strength, and the last is combination load. For the Q factor is the value is used to calculate the allowable state, which is used for the nominal load of co-form steel with perforations. It comes from the stock column test, can tell the efficiency of the co-form steels, and also can be determined from the calculations. Q factor can be determined from the formula by using the ratio of effective area and cross-section area, or the critical local bucking strength and use rate of the co-form steel respectively. For the IMI standard, it focused on T topic too. There are elastic section of the effective sections in two cases, SC and SE, and the largest effective area for the storage lag. You can see the formula on this slide. For the purpose is the first, study the behavior of co-form steel of omega section in full section and perforated section according to AISI and IMI standard. And the second is analyze the allowable load appropriate on each sections with full section and perforated sections. In this slide, it talk about study reliable. We forgot on co-form steel. We have to still get Q factor, steel size, and eccentricity. For the eccentricity is the distance that forward act far from center gravity of cross-section cause moments on surface of columns, with higher amount of eccentricity effect decreasing load capacity of columns.
For methodology, we will calculate the full section by AISI standard. We calculate in program CFS that you can see in the right-hand side. We will get the properties of each section and allowable load in full section. Next, we will calculate the allowable load in perforated section by AISI and IMI standard. With this Q factor, apply the IMI standard to both section modulus and effective area. This part is our result from analyzed data. This graph shows the relationship between allowable load and Q factor with steel grade Q2T5B in different heights, 150 cm and 230 cm at thickness 3 mm. It can be seen that section 120 multiplied 120 can get an allowable load higher than section 100 multiplied 80 in all eccentricity. At both sections, allowable load decreased slightly from Q factor 1 to 0.85 with no eccentricity, which graph tend to be a linear line. Anyway, load with eccentricity value make the moment on columns, then make allowable load decreasing as curved lines, which can be seen in eccentricity at 0.5 cm and 1 cm. So the eccentricity has a high effect on columns, which decrease the load capacity highly when the sections are perforated. For steel grade G450, 10 of all sections in all eccentricity is similar to previous figures. Also, the eccentricity on any cross-section area is a return effect on allowable load, while steel rack height is high. As you can see, a return gap between lines in the graphs. These figures show the relationship between allowable load and height with steel grade Q2T5B in different eccentricity 0, 0.5, and 1 cm at thickness 2 mm. Overall, the load capacity of both sections in both graphs get a decreased trend along increasing height. During the Q factor go down in cross section in the perforated column, it can be seen that Q factor has a high effect on load capacity in any section, which makes a large gap between Q factor at 1.85 and 0.95, or can steadily reduce until height 210 cm before decreasing highly in height 330 cm, which makes graph tend to curve. They are in range of the inelastic curve. Anyway, for steel gauge G450 in section 100 multiply 80, the graphs are at the turning point between the inelastic and elastic curve, which display in a linear line, but the rest is the same behavior.
The relationship between allowable load and eccentricity with grade of steel at Q235B, height 150 and 330, and the thickness is 2 mm. Overall height 150 experience a downward trend, while height 330 cm undergo a stable trend. In height 150, eccentric has a high influence on load capacity, which drops significantly. On the other hand, height 330 cm, changing eccentricity has a small effect on load capacity, causing a stable trend, as you can see in the left figure. And we also notice that the effect of high influence decreasing load capacity, which is more impactful than the effect from eccentricity. As you can see in this slide, displayed allowable load and eccentricity in grade G450, height 150 and 330 cm with thickness is 3 mm. Contributing, we know two things. One is that the effect of Q factor at full section contribute to the allowable load going down across the given eccentricity, whereas that of Q factor at 0.85 and 0.95 lead to the value remaining constant in case of perforation. And the second case is the grade of steel affect the use strength of each grade according to the period, with steel gauge Q235B and this line with steel gauge G450. This contribute that high yield strength has more allowable load than lowest yield strength. And this part is conclusion and recommendation. The conclusion is separated in 5 parts. The first part is the load capacity of cold form steel. Because of perforation in column steel, the load capacity of cold form steel was reduced. And the second part is the Q factor on axial strength. The Q factor contributes the axial strength of column steel lower than the original point, which depends on the size of hole and the number of holes in cross-section area. The third part is the Q factor on nominal moment. Q factor influences both effective section modulus at yield stress and critical lateral marking stress, resulting a decrease in moment capacity in all sections governed by the lateral torsional marking strength failure. The fourth part is eccentricity. The predicted allowable load was identical from the observed experiment result. Normally, the large section can bear more strength than the small section, which result as expected despite negligible decrease caused by eccentricity. But if height of steel lag was increased, allowable load will have little disturbance from eccentricity. And the last one is the grade of steel. The grade of steel has an impact on the behavior of steel, which lead to the value changing rapidly. And the last part is a recommendation. The first one is the section form. Researcher would draw a new section in program to decide depending on the specimen that focus on further research on the preference section on omega section because the cross-section area vary depending on the process of producing cold form steel in any factory. The second one is the value of Q factor and eccentricity. The Q factor and eccentricity value are derived from textbook and are widely used in the market. The suggestion for further study is to use the Q factor and eccentricity in the real world situation where you want to decide. The value should come from the laboratory testing to be more precise and reliable. The third part is just a guideline. The report is a simulation test, not a laboratory test that suggests a guideline for the future testing on the omega section serve as a reference for the design of steel lag in a warehouse and demonstrate the influence of cold form steel preparation using a steel lag. We strongly advise research to test it in the laboratory before using to build in the large structure. And the last one is coarse. Due to the cold form steel has the same size along the cross section and is thin, but the advantage of it is to bear more load compared to the hot rolled steel, and this can cause the cold form steel to have a high price, which contribute to considerable carefully. Thank you.